Well, good morning, physics students. Wednesday, May 27th. Getting down there. Alright, today we're going to talk about simple harmonic motion. And so I would want you to be able to define what simple harmonic motion is and describe what simple harmonic motion is. So, let's start out with a big definition. Simple harmonic motion. It's periodic motion in which the restoring force is proportional to the displacement from equilibrium. Oh boy, there's a lot of words there. Okay, so let's take it apart. Periodic means it's repeating. Restoring force. Okay, so there's a force that's trying to make something go back to an equilibrium position. And the further the displacement, so the further we are from this equilibrium position, the greater that restoring force. I think we're going to need some example to try to truly understand that. All right, so here we've got, this is just, say, a fixed wall and a fixed surface. And for our discussion here, we're going to talk about an idealized situation where this is a frictionless surface. Okay? And we've got a block here, and this block is attached to a spring. So let's imagine that we compress the spring. All right, now I'm going to think about how I want to draw that. So we just compress the spring. Well, when you compress a spring, you got to use a force to compress it, right? And for every force that you apply, there's an equal and opposite force. And you remember back in our energy chapter when we had the Hooke's law apparatus, it was just that little platform hanging on a spring. And the more weight you put on to the platform, the longer it stretched. And so weight is a force also. So the more weight, the more force, the longer it's stretched. In this case, I'm not stretching, I'm compressing, but the same sort of thing. The more we compress it, so I'm going to back up here. Let's go back to this. This represents our equilibrium position. So if I start compressing this, if I push this a little bit in, I get a little bit of force back. The more I push it, the more force back. So when I'm out here, if we were looking at the force, at this position, maybe I got a force like this. If it were over here, maybe I only got a force like this. And if it were here, maybe I only got a force like this. If it's here, how much force do I have? Well, the spring is not compressed, so there's no force whatsoever. Now, what if we move it out further? Okay, so let me try to draw. Oh well, I'm trying. Well, now the force is back this way. And if it were in here, the force would be a little less. And if it were in here, the force would be a little less. And if it's in here. So as this thing bounces back and forth, if you can imagine that we take this, let's say I stretch it out here. Now there's a restoring force trying to pull it back. And the force is going to be big. What does a force do to an object? Force causes acceleration. So at this point, there's an acceleration back this way. Now, as it's moving this way, the force is a little less, the acceleration is a little less. But it's still moving. Force is less, acceleration is less. When it gets here, there's no force. But it's been accelerated this far, so this is where it's moving the fastest. So what happens is inertia moves it past, and so now the object keeps moving and it compresses. Now the force is back this way, a little bit of force. So it's slowing down, right? There's a negative acceleration, and if it keeps moving, it's slowing down on more. The force is bigger, the acceleration is bigger, but it's a negative acceleration back that way. And eventually it slows to a stop. For an instant, it stops. The force is this way. This is where we have, now, this is where students have trouble. The instant at which it stops moving, because it was moving this way and now it's going to start moving this way. So there's an instant at which it stops moving. That's when the acceleration is the greatest, because acceleration isn't about the movement, it's about the change in the movement. And it was just moving that way, now it's going to start moving that way. That's a big change. The force is always directed towards the middle. So this right here, the displacement, the maximum displacement is called the amplitude. All right, and at its maximum amplitude, okay, at that maximum displacement, that amplitude, the force is at a maximum and the acceleration is at a maximum, but the velocity is at a minimum. When we get back to this side, the force is going to be at a maximum, the acceleration is going to be at a maximum, the velocity is going to be at a minimum. Now, at the equilibrium position, the force is going to be zero. The acceleration is going to be zero, but the velocity is going to be at a maximum. That's simple harmonic motion. So if this is a frictionless surface, and let's say somehow there were no internal friction in that spring, this thing would just sit here and oscillate back and forth. All right, how about a pendulum? Well, we know with the pendulum that gravity's pulling down, and so there would be a component of gravity pulling back towards the middle. That's a terrible diagram. I'm going to try it again. Gravity's pulling down. That's not much better than the first one, sorry. Now, what if I took this and swung it out further? Okay, gravity's pulling down. Can you tell that that one should be bigger than that one? What if I had a really small angle? Gravity's pulling down. The force gets smaller. The force gets bigger as we get further away. Now, there is a little problem in here. That these forces, they start to get more and more angled. I mean, if it's over here, the force is going to be this way, not back towards the center. So what we say is a pendulum, if we look at just this small angle region, approximates simple harmonic motion. Because essentially the force is pulling us back, pulling us back. The force is proportional to the distance. The further we get away, the more the force is that's pulling us back. So a pendulum is an approximation of simple harmonic motion. The maximum force is going to be out here at the amplitude, maximum amplitude. The maximum acceleration is going to be out here. Minimum velocity. It's going to get slower as it comes out here. As it goes back towards the center, its maximum velocity is when it passes the center, but that's where there's zero force and zero acceleration. yesterday we dealt with the term period, which is given a capital T, and that is the amount of time for one oscillation. Hope we spelled that right. Okay. There's a term called frequency. And we'll use F here. In chemistry, you might remember we used the Greek letter nu. I'm going to use F for frequency right here. This is the number of oscillations per time. They're reciprocals of each other. So what we have is period is 1 over frequency, or frequency is 1 over period. Let's say that I count 47 oscillations in, let's see, how about 32 seconds. Okay? You think about how I could put those together. I could have 47 oscillations, and that's just a number, per 32 seconds. That's the number per second. That's going to be a frequency. Number per second. And if we divide that out, 47 divided by 32 equals, this is about, I guess I only got 2 sig figs with this, so this would be 1.5 per second. It would be 1.5 oscillations happening per second. Now, there's another way we could write that, 1.5 inverse seconds. 1.5 hertz. A hertz is a unit of frequency equal to an inverse second. So if you ever hear hertz, you can replace it with per second. Okay? What if I flip those two numbers over? If I took 32 seconds for the 47 cycles, let's see, 32 divided by 47 equals 0.68. If you think about the labels on that, would just be seconds. It's that many seconds for an oscillation, so that would be the period. So they're just reciprocals of each other. All right. That's at least a little intro to simple harmonic motion and a few terms dealing with it. So I'll have you do a couple of questions.